The Ising model, named after the physicist Ernst Ising, is a mathematical model of ferromagnetism in statistical mechanics. The model consists of discrete variables that represent magnetic dipole moments of atomic spins that can be in one of two states. The spins are arranged in a graph, usually a lattice, allowing each spin to interact with its neighbors. The model allows the identification of phase transitions, as a simplified model of reality. The two-dimensional square lattice Ising model is one of the simplest statistical models to show a phase transition. The Ising model was invented by the physicist Wilhelm Lenz, who gave it as a problem to his student Ernst Ising. The one-dimensional Ising model has no phase transition and was solved by Ising himself in his 1924 thesis. The two-dimensional square lattice Ising model is much harder, and was given an analytic description much later, by Lars Onsager. It is usually solved by a transfer matrix method, although there exist different approaches, more related to quantum field theory. In dimensions greater than 4, the phase transition of the Ising model is described by mean field theory. Definition: consider a set of lattice sites lambda, each with a set of adjacent sites forming a d-dimensional lattice. For each lattice site k lambda there is a discrete variable sigma k such that sigma k plus 1, minus 1, representing the site's spin. A spin configuration, sigma equals k lambda, is an assignment of spin value to each lattice site. For any two adjacent sites ij lambda 1 has an interaction jij. Also a site j lambda has an external magnetic field Hj interacting with it. The energy of a configuration sigma is given by the Hamiltonian function where the first sum is over pairs of adjacent spins. The notation less than ij greater than indicates that sites I and j are nearest neighbors. The magnetic moment is given by micro. Note that the sign in the second term of the Hamiltonian above should actually be positive because the electron's magnetic moment is antiparallel to its spin, but the negative term is used conventionally. The configuration probability is given by the Boltzmann distribution with inverse temperature beta 0, where beta equals -1 and the normalization constant is the partition function. For a function f of the spins, one denotes by the expectation of f. The configuration probabilities p beta represent the probability of being in a state with configuration sigma in equilibrium. Discussion: the minus sign on each term of the Hamiltonian function h is conventional. Using this sign convention, the Ising models can be classified according to the sign of the interaction. If, for all pairs I, j, the interaction is called ferromagnetic, the interaction is called antiferromagnetic. The spins are non-interacting, otherwise the system is called non-ferromagnetic. In a ferromagnetic Ising model, spins desire to be aligned. The configurations in which adjacent spins are of the same sign have higher probability. In an antiferromagnetic model, adjacent spins tend to have opposite signs. The sign convention of H also explains how a spin site J interacts with the external field. Namely, the spin site wants to line up with the external field. If the spin site J desires to line up in the positive direction, the spin site J desires to line up in the negative direction. There is no external influence on the spin site. Simplifications Ising models are often examined without an external field interacting with the lattice, that is, H equals 0 for all j in the lattice lambda. Using this simplification, our Hamiltonian becomes: when the external field is everywhere 0, H equals 0. The Ising model is symmetric under switching the value of the spin in all the lattice sites. A non-zero field breaks this symmetry. Another common simplification is to assume that all of the nearest neighbors less than ij greater than have the same interaction strength. Then we can set jij equals j for all pairs I, j in lambda. In this case our Hamiltonian is further simplified to questions. A significant number of statistical questions to ask about this model are in the limit of large numbers of spins. In a typical configuration, are most of the spins +1 or -1, or are they split equally? If a spin at any given position I is 1, what is the probability that the spin at position j is also 1? If beta is changed, is there a phase transition? On a lattice lambda, what is the fractal dimension of the shape of a large cluster of +1 spins? Basic properties and history. The most studied case of the Ising model is the translation invariant ferromagnetic zero-field model on a d-dimensional lattice, namely, lambda equals zd, jij equals 1, h equals 0. In his 1924 PhD thesis, Ising solved the model for the d equals 1 case, which can be thought of as a linear horizontal lattice where each site only interacts with its left and right neighbor. In one dimension, the solution admits no phase transition. Namely, for any positive beta, the correlations less than sigma I sigma j greater than decay exponentially in I minus j, and the system is disordered. On the basis of this result, he incorrectly concluded that this model does not exhibit phase behavior in any dimension. The Ising model undergoes a phase transition between an ordered and a disordered phase in 2 dimensions or more. Namely, the system is disordered for small beta, whereas for large beta the system exhibits ferromagnetic order. This was first proven by Rudolf Peierls in 1936, using what is now called a Peierls argument. The Ising model on a 2-dimensional square lattice with no magnetic field was analytically solved by Lars Onsager. Onsager showed that the correlation functions and free energy of the Ising model are determined by a non-interacting lattice fermion. Onsager announced the formula for the spontaneous magnetization for the 2-dimensional model in 1949 but did not give a derivation. Yang gave the first published proof of this formula, using a limit formula for Fredholm determinants, proved in 1951 by Shigo in direct response to Onsager's work. Historical significance. One of Democritus' arguments in support of atomism was that atoms naturally explain the sharp phase boundaries observed in materials, as when ice melts to water or water turns to steam. His idea was that small changes in atomic scale properties would lead to big changes in the aggregate behavior. Others believed that matter is inherently continuous, not atomic, and that the large-scale properties of matter are not reducible to basic atomic properties. While the laws of chemical binding made it clear to 19th-century chemists that atoms were real, among physicists the debate continued well into the early 20th century. Atomists, notably James Clerk Maxwell and Ludwig Boltzmann, applied Hamilton's formulation of Newton's laws to large systems, and found that the statistical behavior of the atoms correctly describes room temperature gases. But classical statistical mechanics did not account for all of the properties of liquids and solids, nor of gases at low temperature. Once modern quantum mechanics was formulated, atomism was no longer in conflict with experiment. But this did not lead to a universal acceptance of statistical mechanics, which went beyond atomism. Josiah Willard Gibbs had given a complete formalism to reproduce the laws of thermodynamics from the laws of mechanics. But many faulty arguments survived from the 19th century, when statistical mechanics was considered dubious. The lapses in intuition mostly stemmed from the fact that the limit of an infinite statistical system has many 0-1 laws which are absent in finite systems. An infinitesimal change in a parameter can lead to big differences in the overall aggregate behavior, as Democritus expected. No phase transitions in finite volume in the early part of the 20th century. Some believed that the partition function could never describe a phase transition, based on the following argument. The partition function is a sum of E minus beta E over all configurations. The exponential function is everywhere analytic as a function of beta. The sum of analytic functions is an analytic function, but the logarithm of the partition function is not analytic as a function of the temperature near a phase transition, so the theory doesn't work. This argument works for a finite sum of exponentials. and correctly establishes that there are no singularities in the free energy of a system of a finite size. For systems which are in the thermodynamic limit, the infinite sum can lead to singularities. The convergence to the thermodynamic limit is fast, so that the phase behavior is apparent already on a relatively small lattice, even though the singularities are smoothed out by the system's finite size. This was first established by Rudolf Peierls in the Ising model. Peierls droplets shortly after Lenz and Ising constructed the Ising model. Peierls was able to explicitly show that a phase transition occurs in 2 dimensions. To do this, he compared the high temperature and low temperature limits. At infinite temperature, beta equals 0, all configurations have equal probability. Each spin is completely independent of any other, and if typical configurations at infinite temperature are plotted so that plus, minus are represented by black and white, they look like television snow. For high, but not infinite temperature, there are small correlations between neighboring positions. The snow tends to clump a little bit, but the screen stays random looking, and there is no net excess of black or white. A quantitative measure of the excess is the magnetization, which is the average value of the spin. A bogus argument analogous to the argument in the last section now establishes that the magnetization in the Ising model is always 0. Every configuration of spins has equal energy to the configuration with all spins flipped. So for every configuration with magnetization m, there is a configuration with magnetization minus m with equal probability. So the magnetization is 0. As before, this only proves that the magnetization is 0 at any finite volume. For an infinite system, fluctuations might not be able to push the system from a mostly plus state to a mostly minus with a non-zero probability. For very high temperatures, the magnetization is 0, as it is at infinite temperature. To see this, note that if spin A has only a small correlation epsilon with spin B, and B is only weakly correlated with C, but C is otherwise independent of A, the amount of correlation of A and C goes like epsilon 2. For 2 spins separated by distance L, the amount of correlation goes as epsilon L, but if there is more than one path by which the correlations can travel, this amount is enhanced by the number of paths. The number of paths of length L on a square lattice in d dimensions is, since there are 2D choices for where to go at each step. A bound on the total correlation is given by the contribution to the correlation by summing over all paths linking 2 points, which is bounded above by the sum over all lengths paths of length L divided by which goes to 0 when epsilon is small. At low temperatures, beta 1, the configurations are near the lowest energy configuration, the one where all the spins are plus or all the spins are minus. Peierls asked whether it is statistically possible at low temperature, starting with all the spins minus, to fluctuate to a state where most of the spins are plus. For this to happen, droplets of plus spin must be able to congeal to make the plus state. The energy of a droplet of plus spins in a minus background is proportional to the perimeter of the droplet L, where plus spins and minus spins neighbor each other. For a droplet with perimeter L, the area is somewhere between 2 and 2. The probability cost for introducing a droplet has the factor E minus beta L, but this contributes to the partition function multiplied by the total number of droplets with perimeter L, which is less than the total number of paths of length L, so that the total spin contribution from droplets, even overcounting by allowing each site to have a separate droplet, is bounded above by which goes to 0 at large beta. For beta sufficiently large, this exponentially suppresses long loops, so that they cannot occur, and the magnetization never fluctuates too far from -1. So Peierls established that the magnetization in the Ising model eventually defines superselection sectors, separated domains which are not linked by finite fluctuations. Kramer's one-year duality. Kramers and one-year were able to show that the high-temperature expansion and the low-temperature expansion of the model are equal up to an overall rescaling of the free energy. This allowed the phase transmission point in the two-dimensional model to be determined exactly. Yang-Li zeros after Onsage's solution. Yang and Li investigated the way in which the partition function becomes singular as the temperature approaches the critical temperature. Monte Carlo methods for numerical simulation. Definitions. The Ising model can often be difficult to evaluate numerically if there are many states in the system. Consider an Ising model with L lattice sites. Let L equals lambda, the total number of sites on the lattice, sigma j minus 1 plus 1, an individual spin site on the lattice, j equals 1, L, s minus 1 plus 1, L. State of the system. Since every spin site has plus or minus 1 spin, there are 2 L different states that are possible. This motivates the reason for the Ising model to be simulated using Monte Carlo methods. The Hamiltonian function that is commonly used representing the energy of the model when using Monte Carlo methods is. Furthermore, the Hamiltonian is further simplified by assuming zero external field, since many questions that are posed to be solved using the model can be answered in absence of an external field. This leads us to the following energy equation for state sigma. Two such examples of estimates of interest are the specific heat or the magnetization of the magnet at a given temperature. The Metropolis algorithm. Overview of algorithm. The Metropolis-Hastings algorithm is the most commonly used Monte Carlo algorithm to calculate Ising model estimations. The algorithm first chooses selection probabilities G, which represent the probability that state nu is selected by the algorithm out of all states. Given that we are in state mu, it then uses acceptance probabilities A so that detailed balance is satisfied. If the new state nu is accepted, then we move to that state and repeat with selecting a new state and deciding to accept it. If nu is not accepted, then we stay in mu. This process is repeated until some stopping criteria is met, which for the Ising model is often when the lattice becomes ferromagnetic, meaning all of the sites point in the same direction. When implementing the algorithm, we must ensure that G is selected such that ergodicity is met. In thermal equilibrium, a system's energy only fluctuates within a small range. This is the motivation behind the concept of single-spin flip dynamics, which states that in each transition, we will only change one of the spin sites on the lattice. Furthermore, by using single-spin flip dynamics, we can get from any state to any other state by flipping each site that differs between the two states, one at a time. The maximum amount of change between the energy of the present state, h mu, and any possible new state's energy, h nu, is 2j between the spin we choose to flip to move to the new state and that spin's neighbor. Thus, in a 1D Ising model, where each site has two neighbors, the maximum difference in energy would be 4j. Let C represent the lattice coordination number, the number of nearest neighbors that any lattice site has. We assume that all sites have the same number of neighbors due to periodic boundary conditions. It is important to note that the Metropolis-Hastings algorithm does not perform well around the critical point due to critical slowing down. Other techniques such as multi-grid methods, Niedermeyer's algorithm, Svensen-Wang algorithm, or the Wolf algorithm are required in order to resolve the model near the critical point, a requirement for determining the critical exponents of the system. Algorithm specifications. Specifically for the Ising model and using single-spin flip dynamics, we can establish the following. Since there are L total sites on the lattice, using single-spin flip as the only way we transition to another state, we can see that there are a total of L new states nu from our present state mu. The algorithm assumes that the selection probabilities are equal to the L states. G equals 1, L. Detailed balance tells us that the following equation must hold. Thus, we want to select the acceptance probability for our algorithm to satisfy. If h nu greater than h mu, then A greater than A. Metropolis sets the larger of A or A to be 1. By this reasoning, the acceptance algorithm is The basic form of the algorithm is as follows. Pick a spin site using selection probability G and calculate the contribution to the energy involving this spin. Flip the value of the spin and calculate the new contribution. If the new energy is less, keep the flipped value. If the new energy is more, only keep with probability. Repeat. The change in energy h nu minus h mu only depends on the value of the spin and its nearest graph neighbors. So if the graph is not too connected, the algorithm is fast. This process will eventually produce a pick from the distribution. Viewing the Ising model as a Markov chain, it is easy to view the Ising model as a Markov chain, as the immediate future state new transition probability, p beta, only depends on the present state mu. The Metropolis algorithm is actually a version of Markov chain Monte Carlo simulation, and since we use single-spin flip dynamics in the Metropolis algorithm, every state can be viewed as having links to exactly L other states, where each transition corresponds to flipping a single spin site to the opposite dipole. Furthermore, since the energy equation H sigma change only depending on the nearest neighbor's interaction influence J, we can view the Ising model and its variations such the SZNAJD model as a form of Voter model for opinion dynamics.